Okay, thanks. Thank you. Yeah, so part of the reason I put this up, well, first off, thank you all for joining me today and spending your Friday with me. And everyone online, thank you as well. I can actually hold you look at that camera. Thank you very much. Yeah, so throughout this presentation, I'll be asking like polling questions. And if you'd like to participate, please scan the barcode. It'll be on every one of the slides that we ask questions. It's not so important, but just if you want to give me your opinion. And based on the current survey results, the things people like are my talk, machine unlearning, GPT-4 seems quite popular, k-means, bounds, gradient descent. Yes, all good ideas. All right. Okay, so I can figure out how to do this next AI system. All right, yeah, so there's all that information again, just a little bit bigger if your phone can't detect the previous one. Right, so today I'm going to be doing a presentation called Advances in Data-Driven Teleoperation, a synthesis of previous works and our own, which is basically just kind of a summary of previous works that people have done and what we've done to add to the literature so far. So, well, just to kind of add to Martin's thing, these aren't so important, but yeah, so I'm a fifth-year PhD student here at U of A, where I work at the intersection of machine learning and robotics. I am co-supervised by the talented Dr. Martin Jagerstand of the Computer Vision and Robotics Group, and the also equally talented Matthew Taylor with the Intelligent Robot Learning Lab. And I oftentimes collaborate with this guy at the University of Innsbruck, Dr. Samuele Casado, who's affiliated with the Intelligent and Interactive Systems Group. And so one thing I just want to point out, if you look at all these photos, is that all these men are wearing blue shirts. And so too must I continue this tradition of wearing blue shirts for my presentations, and so too will my students and their students after them. So just to kind of set the things that I hope you take away from this presentation, you're going to learn what is data-driven teleoperation. I'm going to do this for a second so I can actually not keep looking that way. I didn't show it. No, yeah, always. How to build a data-driven teleoperation system. I apologize to those of you who aren't deep learning experts, but there is kind of a certain base knowledge that I am assuming, so I apologize. But once you have those things, then this knowledge will be useful to build your own systems. And what are some research directions of data-driven teleoperation? And, you know, kind of giving you ideas of what people have done and what are promising future directions, I think, in case you're thinking of grad school or looking for a research topic or something. So part of the reason I decided to do this presentation like that, I'm going to motivate with the actors from, I believe it's the TV show American Horror Stories. So, you know, when I started looking into this and kind of using the actors, you know, you look at one of these actors and you're like, wow, this is so great, handsome guy. I'd really like to know the rest of the cast. And then you kind of start going through all the literature and all the literatures, and you kind of start seeing there's a lot of commonalities between them. And given all these similarities, you know, you can kind of like, to get a bigger picture and sense of what's going on, you can kind of see there's a lot of carryover between these things, right? So I thought like, well, it'd be good to kind of try to share and summarize all the like differences between these different papers into a single topic to kind of paint the research. And so what that is going to look like is I'm going to try to summarize and share the important parts from 9 different papers. The last 2, I think, are mine, if I remember the ordering that I put. And for those interested, let me know and I can send you the slides and you can take a look at any of them if you're interested by any of these ideas. Right. So to kind of set the stage about what data-driven teleoperation is. So the way it looks, at least in our research, is there's a person, there's a joystick, and they're moving the robot with the joystick. And if you don't remember anything or don't understand anything, that is the end product of what we are doing in this line of research. Is we want to do some sort of mapping between some sort of control interface, so this joystick, to move a robot to do more complex tasks. So why might we want to do this? Is a very important question. So the original motivating domain is assistive robotics, where this video is showing people living with disabilities who rely on robot arms to do daily tasks. So they kind of rely on this thing to do their day-to-day tasks. And this is, you know, video footage from previous work of a colleague, Laura Petridge. So robotic teleoperation systems can help patients perform daily tasks. And current systems use what is called mode switching in order to control the robot, where we select and control a few aspects of the robot at any time. If you don't know anything about robots, well, they have joints. So one way you can think about it is you can control a subset of joints at any moment, or you can think about it as controlling the pose of the robot. And what this table is showing is kind of what mode switching might look like in practice. So for those who don't know, there's a lot of math and stuff that explains that there's a coordinate system that can explain an important part of the robot. And so the way mode switching works is that, like, if you have a 2D joystick, so you can only move in 2 directions, at any moment you might be corresponding to, like, say, if I'm in mode 4, like the XY plane, so I can only move in a plane like this. Then I click a button, and then maybe I'm moving in the XZ plane, so moving like this. Click again, and then I'm moving in the, what did I put on there? The ZY, I think like this, right? And so we're only ever controlling a subset of the maximal things that we control with the robot. Now, the issue with this, though, is that this can be a bit mentally demanding. Some previous papers have reported that it can require anywhere from like 30 to 60 cycles between the different configurations of the robot that you want to control to do day-to-day tasks. And, you know, usually in day-to-day, we're going to do a lot of the similar motions. And so you have to kind of go through this cycling process in order to do, you know, simple tasks like paying with your credit card, which was shown in the video, or pouring in class. That can be a bit tedious and be mentally taxing. And so, you know, kind of maybe interfere with your quality of life. So the question we kind of pose then is that, you know, here we work in some sort of coordinate system of this robot thing, right? So X, Y, Z, and pitch, yaw, roll. So instead, what if we think about it more as, instead of thinking about like X, Y, Z coordinates or something, we think of it as more like we want each direction to correspond to a movement. So instead of up and down corresponding to doing something like this, maybe up and down corresponds to like me reaching towards my mouse, and then left and right corresponds to me picking up and throwing it or something. Yeah, skip a bit. Anyways, and so that's kind of the idea of what we want to do. Instead of thinking of aspects of robot control, can we just directly map things people want to do to the joystick itself? So that's like the big picture motivation and question. But, you know, one might wonder, okay, that's great, but why are you specifically, Michael, doing all this stuff? So I don't take any big hoity-toity visions of this and that. I heard about this topic from a previous colleague, and kind of following the pattern of Marge Simpson with potatoes, I just thought it was neat, so I started digging into it. I started re-implementing some works and stuff, and I found that there were some problems I didn't like, and so that kind of started to become my research. And so this video highlights the problem that I identified when trying to follow previous works, where we have a person using a joystick here, and he lets go, and the robot keeps moving. So there's a lot of deep philosophical important questions when it comes to AI research. And for me, the starting point for those very deep and important questions was, how do I stop this thing from moving it? And so I have complete control over it. I will point out this is also why it's important to, you know, recreate other people's work, because if I just took what they said in the paper for granted, I would never have found this problem and gotten funding and stuff to go and look into it for years. So the kind of bigger thing from that question, though, is that one thing I also noticed was missing in the literature is there's a lot of empirical work saying, yeah, this is a good idea. Here's the thing working, but I didn't see as much work saying, okay, here's what I can say. If you make these assumptions about the model, here's kind of what you can expect to happen when you deploy it in the real world. And although I'm not too familiar with like how to get sort of government approvals for things and stuff, my general sense is that if I can say, here's my learning system, there are aspects which we don't really know how it's going to work per se, just because, you know, it's a learning and nonlinear model or whatever. But if I can say some concrete things like, hey, if my model has this, this, and this, and it will have these guarantees, I think that's a much stronger thing and helps us like understand what we're doing, debug it, and make it build trust with the system to deploy, right? Right. So it's easier to deploy a system if we could say more concrete things about it that are just by design as opposed to we empirically evaluated, and it happened to work this way. So just to kind of now formalize the setup a little more. So we start with this joystick, which we've been talking about. The joystick has 2 directions, up, down, left, right for our experiments, but you can imagine different setups, of course. You have some sort of high dimensional control interface, which is, in this case, the 7 joints of what is called a Canova Gen 3 Lite in our lab. And in between, we have some magical black box thing that we call the action mapping function that we are going to try to learn in order to, you know, do teleoperation. Now, just kind of for fun, at this point, I haven't really told you how we're going to do it, and I think I already gave it away, but just for fun, I'll give a minute just to send it to the audience. What do you think might be a way we could solve this? So if you have any ideas about like algorithms, methods, or give your whole anecdote, this is your time to give your 2 cents. Deep learning magic. Yep, that's a very promising one. I don't want to spend too much time, so I'll give it 30 seconds. Feature selection. So we need to do something clever about how we structure the systems. True. trajectory optimization, variational inference. It's a cool idea. I do like VI. Cool. All right, and I think that's all we got. And so these are all great ideas. And part of the reason I thought I would ask this is because other times I presented this work, I've heard of a lot of great ideas from the audience about other ways that this could be solved or you could investigate it. And I think they're all promising. For the sake of this presentation, I appreciate who wrote this. We are going to take the deep learning magic direction, of course. But all these other ones are promising, and there are other methods that you could accomplish similar things, just to be clear. So we said that there's lots of different ways. We decided we're going to take the deep learning route. And so a very simple question then is like, okay, you want to do these action mapping things, but do they actually make a difference, like empirically? So here in previous results, somebody has compared a shared autonomy algorithm, which is just like another way to kind of control a robot in order to do something. And they compared it against an action mapping algorithm, which is this thing in orange. So what these plots are trying to communicate is that by these different means that lower is better. And so what these plots are kind of showing us is that, you know, in terms of task completion, so how long it takes you to do whatever the underlying task that they were doing, took less time, it required less input from the user. So this is kind of addresses this issue of cognitive load by minimizing how much interaction the person needs with the system. And we see that they also had shorter trajectories. So like by all these different metrics, what we seem to be finding is that action mapping seems to be quite a good idea, and that there might be, maybe shared autonomy algorithms don't work quite as well as action mappings, at least according to previous books.
So what is shared autonomy?
Shared autonomy, I have a slide that talks about it at a high level, but the gist of it is like a person, so first off, I don't work in shared autonomy, so I apologize if someone does and I'm butchering the field, but my understanding of it is someone's controlling the robot to do something, and over time, the robot is kind of watching them do it. And can help the person complete the task. So like, I guess one way I could see it being done that isn't related to joysticks is like, maybe you have like an exoskeleton or something, so you need help walking. So then it would kind of adjust, and like if you want to do a walking gait or something, it would kind of compensate for what's missing in your muscular strength or something. And if that's not what shared autonomy is, I'm sorry, but it's how I can understand it. Martin, you seem to have a thought?
Yeah, there are many. I mean, it's a very broad field.
Yeah.
One example could be that the robot and a person, you know, carries each end of a piece of furniture, so that the robot has to kind of sense through the piece of furniture what the human's doing, and then react appropriately, right? So that they can, say, navigate through some doors and upstairs.
I see.
But then there are many others, more akin like what Michael said, right? That where gradually the system learns from the human what the human does, and then provides kind of assistance along the same freedoms as opposed to doing a different task, right?
Okay, thank you, Martin, for that. Sorry, I was just looking at the survey thing. Yeah, so this one thing I forgot to mention is throughout this presentation, I'll have slides that say pause. And if any questions come up for what we just talked about or anything previously that you have questions about, now would be a good time to ask. So if anything didn't make sense, or even just little clarifying things like what does this symbol mean, happy to answer. I want to make sure everyone is following along as best they can. So in the chat, I had one comment, paper 2 and 5 are not the same. I don't think paper 2 and 5 were the same inside. I'm not going to go back to check. Right. Cool. So we've established the problem that we want to solve and why it might be interesting. So how, at a very high level, might we go about learning these action mapping functions? So we're doing deep learning. And so in deep learning, there's a framework called the conditional autoencoder, where we have two models, encoder and decoder, and they're both going to take in some sort of observation OR here as part of their inputs. And I'll explain what OR is on later slides because that's one of the research areas of this topic. So the encoder is going to map velocities to latent actions. This notation will change throughout the presentation, so I apologize to everyone, but X dot, so we're always, whatever the robot's doing, it's always going to be robot velocity commands, at least in the literature we look at. So X dot is going to go through this model plus OR. This is going to be compressed into some sort of low dimensional control action. So those would be things that the person is actually sending to the robots. And that is all the encoder does. And we don't really care too much about it because we're going to throw it away anyways at deployment. The thing that we care about, and that is the action map that we are going to deploy, is the decoder part. Because what the decoder does is take in the action and the observation and then remaps it to the velocity commands. And so that's how we're getting this low to high projection mapping that a person is going to interact with. And so one thing that is going to be important later is that either people usually use what is called a multi-layer perceptron, a typical like feed-forward neural network, or they use, or what we propose is using is what is called a hyper network. And if you don't know what a hyper network is, I'll expand on it later. And if you don't know what a MLP is, I apologize, I'm not going to explain it. But it's a neural network, it's a type of AI ML model. So, we say the state conditioning is important, but like why do we need state conditioning in this context? So generally actions need to be defined in some sort of context, right? You could hypothetically just do whatever you want arbitrarily, but in order to complete some sort of problem, take up the cup, open the door, there's some sort of important information that we care about in order to complete that task. So, it doesn't really make sense to try to pour from a cup if you're far away from the cup. And so the reason we do this is it limits the possible behaviors to the specific task of interest. Another way I think about this is that since we only have a few degrees of control, and we're trying to control a very high dimensional complex system, you can't do everything as freely as you want. And so having this additional information kind of discriminates to compensate for the loss of control that you have due to this low to high projection, right? So what this looks like according to experiment results from previous work again. So we have two robots here, gray robot, orange robot. So gray robot has no state conditioning and orange is state conditioned. And the task that we're trying to do here is there's this line and we'd really like to follow that line. And so in order to follow that line, we need to know where is the line, where are we, and then we can kind of adjust as necessary to follow the task. And so what they show here is that, without any sort of useful state conditioning or like incomplete, unhelpful partial observations, the robot is unable to follow the task, right? It's a very simple problem, but even in the simple setting, it's unable to do it without the appropriate information. Whereas as soon as we add what the task is, it's able to easily follow it, right? And so clearly, at least based on this very toy example, it seems to make a difference having additional information about the problem we would like to address.
Gray doesn't have that dotted line.
No, gray does not.
How will it solve it then?
That's the issue I'm describing exactly. It can't, because it doesn't know what it's trying to do. So yeah, exactly what you're saying is that's why it's impossible or hard for the gray mapping to solve this task, because it has no information about what it's trying to do.
Impossible, right? Impossible.
It might be possible. It might be possible, but that required a lot more math than I had time to investigate, and it would probably require a very weird, bizarre way in order to do it, if it was even feasible. So I'll take another pause. If anyone has any questions. Okay.
Without state conditioning, maybe you're given the problem at the very beginning and then you're not told how your robot looks, what are the joint positions at each point. Like what is state conditioning?
State conditioning,
Yeah, I'm conditioning my policy is conditioned on my states. Is it
Yes.
that?
yeah, so you can think of it like that.
As opposed to just a policy which is
So the
State
difference between,
independent.
so one way, if you want to go with the RL perspective, is that like action mappings are a way of, doing low to high projection mappings. So you still want to give all the control to the thing that's actually sending the inputs to the model, as opposed to the more typical end-to-end policy, where we have full degree like control of every single action. So it's this intermediate model that we're not interested per se in like using it. Well, we want it to help us solve the task, of course, but like we're more interested in being able to like get useful actions that we could do the task with, that is then solved by some control policy, where in our context, we say the control policy is a human. Yeah, good questions. Okay. So we have a vague idea at a high level how to train these things. So what are the actual interesting research directions that people have considered in the lexicon or in the papers? So the first part is data conditioning, which includes things like how do we actually collect the data so that we can train the model, and what kind of data should we use as inputs to the system. And then on the other side, we have the actual, what I'm calling system analysis. I think for maybe engineers is a more technical definition, so I apologize. But by system analysis, I'm just saying like, assuming we have a trained system, or what properties do we care about the system having? How do we enforce those explicitly? Or say we have, in the case of the shared autonomy setting, like we have this trained model, how can we use it inside of a bigger system with robotics in order to do something else? So to start, we're going to talk about the data conditioning aspect of it. So I've said that we want to train a system, from velocities, some sort of observations, and back to velocity commands. But what exactly is that data? So to show some of our results, well, this footage is a colleague of mine showing the task we would like the robot to perform. As you can see, he's pushing the robot around in circular motion to wipe a table. And so what he's doing, for those who don't know, is called kinesthetic demonstration. So this is the practice of physically just moving the robot in order to do whatever you want. And robots have a bunch of sensors that can tell you things about where the robot is in the world. So this includes things like, what are the joint values of the robot? How fast is it going? Maybe there's force sensors if you're lucky, position of this coordinate system I mentioned earlier on. So all this is called, I believe, proprioceptive information. And so yeah, manually move the robot to do the task. And so you collect this data set, someone moves the robot, and then do some processing to get your actions and whatever this observation OR is. And that's your data set for training. So some other ways people have thought about it is that maybe manually collecting data is kind of tedious. So you might be an RL guy, you like to do things autonomously. So people have also considered the unsupervised approach. So using some AI model to just automatically generate the data for you. The way this worked in previous papers, they maximize for state entropy, which the way I'm going to say it is you just try to get as much coverage of the world as you can. I just flail around a lot and get everywhere. And we're going to say that's good data. One caveat on that line of research is they say it's unsupervised, but then they still manually specify some target state that this is a good state to visit. So it's unsupervised after you supervise the training pipeline. So the other thing you might care about is, say you have a pre-trained system, you have this model, but a person doesn't like the way it works. So, you're controlling the system, and it is an ongoing problem, to be honest, in this line of work, where it seems unintuitive from a user perspective. So another way you can get data, assuming you've trained the model and you want to make it more personalized for the person, is, so you have the model and robot, and you have the robot. And so you generate some action, and the robot moves. So based on the action that did that movement, you will ask the person, how would you have done that movement? So, Siobhan, since you're sitting right there, if I do this, which direction do you think it should move in order to generate this movement?
Right, up.
Right, up. Okay, so let's say the system generated right to move this movement. He wants it to go up. So then we're going to learn more neural network to map up to right of the internal underlying system. So I guess one way, as I'm saying it out loud, you might think about it as kind of actually, no, that doesn't make any sense. Anyway, the point is you're trying to remap the base system to the preferences of the person. And you do that, at least according to previous works, by querying the person, how would you actually like this to move? And ideally, you'll need even less data than you did to train the original system in order to do this.
So maybe third way is more like reinforcement learning, and second is just creating.
Yeah, well, human in the loop RL, I guess, because you're getting human preference. So it's like human preference learning, I guess. So one thing I think is potential future work is, although these are cute ideas, kinesthetic demonstration is still kind of the most obvious way to collect data. And from my own personal experience, I have found that oftentimes getting good demonstrations can be a very time-consuming thing. If you read a paper, it'll say 5 minutes. You think, cool, and then you spend 5 minutes over 8 hours of the day doing 5 minutes, 5 minutes, 5 minutes, 5 minutes until you kind of get that good data set you actually use deployment. So getting this kind of show once, deploy, I think is still there's room for work to be done in that sphere. Right. So we're going to move on to now, what things should we give the model? So let me make sure that I'm on the right thing. Okay. So hopefully this should be the survey question about what kind of data might make teleoperation easier. So I gave an example, images. So for those who want to participate, what kinds of data do you think we could use for the teleoperation system? And I won't spend too much time, but it's also a good way to figure out what's future work potential. Proprioceptive data, that is correct. Sequences of actions, true. I think there's some work that says it sometimes can be a bad thing. I would have to talk about that too much to make yeah. Human preferences, yes. might be a bit ambiguous of a question, but I want to pretend that's good, because then we get more variety of answers. Human preferences, sequences of actions, proprioception data, images as well, but okay. Cool. So we'll move on now. So these are some promising ideas. Human preferences, as we've talked about, is something people have looked at. Sequences of actions, I don't think has been done. I do kind of think there might be some issues if you do that, but it is possible. And yes, we are going to use proprioceptive data, so that's great. But now, what is the research otherwise explored besides these promising directions that people have proposed in the audience? So one that has been kind of, I think, maybe more typical for like a computer vision guy is visual features. So if you're able to get a camera with your system and kind of look at the scene that you want to do stuff in, it can kind of give you some clues as to what the task is of interest for the person. So in previous works, what they found was that if you use some sort of model, in this case, the YOLO version 5, it's a good idea to extract features that are kind of not neural network specific. So if you don't know what YOLO is, my understanding is like an object localization algorithm or detection thing. So if my hand, your eyes are the camera, and you're looking at my hand, it will produce a bounding box around my hand, say this is a hand, and here are coordinates of where the hand is. So like, 4 XYZ, XY locations on a 2D plane. And if you give those coordinates to the downstream decoding model, those are generally better representations than if you took like a convolutional neural network, got some really dense embedding and fed that to the model. And so generally this like low feature extractions or human pseudo interpretable features are a good idea as inputs to the model. The next thing people have considered is the belief about users' goals. Although shared autonomy, at least as in the previous work, may not be the best, combining it with this approach can also be beneficial, according to previous works. So this I find a bit vague, but there is some sort of shared autonomy line of research where like measures how much we believe the person is trying to do or reach towards certain objects in the scene. And then giving that as input is another useful feature that people have found in the literature. And the last one is text features. So, put the banana away, pick up the bowl, like giving a text description of what you want to do with the system has been something people have also done. And in this line of research, they take some off the shelf, I think, Alberta in this case, get some feature representation, and then they try to feed that meaningfully into the model. But as we pointed out with image features, these kinds of deep learning embeddings can be kind of bad, especially if you don't have much demonstration data. And so what they do to mitigate that is they keep a dictionary of these are the sentences that we have found that the system has seen and knows how to behave. So again, giving what the person actually says. So I would like to grab a cup, but maybe the system hasn't seen, I would like to grab a cup. It'll find the nearest representation it has seen and then feed that in to model that sentence. And that seems to work well, at least empirically. Right. So that's all good ideas. So as we've seen, there's a variety of different kind of input types we might use. And so some promising future directions, I think, are, we might add tactile and force data. So like how much are we pushing into a table or are we touching something, which there are sensors that you can add to a robot is one direction. But really any sort of sensor you could think of, you could probably add to the system. And if you can write a story about why that might be plausible in the real world, you could probably write a paper. LiDAR, maybe something that comes to mind. I don't know if that would be useful, but point is like any sort of data types you could think, graphs, things like that could be hypothetically added, right? One thing though, all that being said, you can collect all these fancy sensor datas, but it still isn't really clear to me if the assumptions we make with how we collect them are ever going to be really valid in the real world. So like, one of the settings we imagine is that you have a person living with a disability, they're in a wheelchair or something, someone comes in and has to do this kinesthetic demonstration. But then you still also need the corresponding pictures mapping to what they just showed. And so it isn't really clear to me how easy that would be in practice. And so kind of, I think, more pragmatic questions of where is this data actually coming from are still kind of relevant. Like the belief paper really confused me because it's like, how are you getting the beliefs about what you think the person's doing? I could imagine ways, but I think it's kind of something that gets washed under the rug a bit too much. And the last one is supposing you have all these different sensors or input types. It is also plausible to imagine in the real world, sensors go down. So maybe today you have a camera, tomorrow you don't. You'd still like the model to work as best as it can in spite of not having additional sensor information or things like that. And so being able to kind of pop in and out of different sensors, I think would be a very powerful thing that remains to be explicitly talked about in the paper so far. So I'm going to pause there. Also, there's a theme to all the titles of this pause slide, so happy to take guesses at the end, but yeah, good time to ask any questions, or if you have any discussion points you'd like to talk about.
Can you talk a bit more about why we would want continuous human interaction, right? So if we have a system where we can say, please put the cup in the dishwasher, wouldn't just that be it, right? Or for what reasons would we want the person to be in the loop?
Yeah, so that's a good question, and I guess, yeah, kind of. So my understanding is that, from what I've heard from other people, is that generally people like to be in control and do things themselves as much as possible. Although I think you raise a good point, and I think that's maybe actually also another area of potential research of doing exactly kind of the setting is like, give the person an option where you say the text description, like put this in the dishwasher, please, and then the robot just takes over and does it for you. And compare it to like them saying the same thing, I want to put this in the dishwasher and then have them manually control it and kind of see what they prefer. So I think that's more, I would say, is on the human side. But I think you raise a very good point where maybe if we already have text descriptions and the model has seen how to do this task, maybe we don't really need the person. But my understanding is people like to kind of do things for themselves. So that's my weak argument for it.
When you're encoding these robot velocities to an action map, what exactly is the action map? Like, what would be an example of an element in that set of actions?
Oh my gosh, I actually did touch it. Sorry. Sorry. I'm just laughing because I was told, like, why would people touch these buttons, and then here I touch the button. Right. So if you know what an autoencoder is, the autoencoder is the thing that does. Sorry, I already forgot the question because it was on the lights. So you're asking, how does it know what is the set of viable actions? Is that correct?
Right, that you're encoding to. So like, what would be an example of an action in that set? So would it be something like, would it be a statement like move 30 degrees up, or would it be something like, I want to put something in the dishwasher? Like, what exactly are these actions that you map into that when you do the decoding get turned into robot velocities?
Okay, so there's a bit of customization that goes with it, because you can, so short answer, it's a vector. So like if you have a 2D joystick, it's a two-dimensional vector of continuous numbers on a bounded set. So, if the joystick goes from 1 to -1, that's the dimension. So up and down is 1 to -1, that's dimension 1. Dimension 2 is left and right from 1 to -1. So what we're encoding is a continuous representation to a continuous representation. So, yeah.
So maybe the dishwasher wasn't the perfect example, but so there is general research that says that humans want to be on control in a robot that works in their closed space. And these assistive robots are literally sitting right next to them on the wheelchair. So if you're not, if the robot sort of does its own thing, you'll never know when it's going to swing in front of your face or something. Another thing is, of course, many of these tasks are not necessarily putting a dishwasher, right? I'd love to if the robot solved that by itself, or even more so, vacuum the house. But it's things like feeding, whereas autonomous systems, they typically learn when to give you food by, they watch your face when you open your mouth, they take the chance to put in some food in the mouth, right? So that they can synchronize, right? It would be very hard with a robot that just stuffs food at a particular rate. But there are many situations when that's inappropriate. So if you're in a social situation, you might just as well open your mouth to talk. And then if you get stuffed with a potato, would not be, an example of human-friendly HRI.
Yeah.
So I think that's one way to think of it. There are so many tasks where we would want to be able to immediately either pace the robot so we can control when we get the food, or stop the robot because the autonomous system somehow couldn't fully figure out what we really wanted to do.
Yeah, I think that's a good point, and it also fits in the motivation of this work of context is important, right? And it's more important now, maybe one point we want the robot to go to our mouth and one part we don't. So, okay, so we're going to continue. All right. Ah, whoops, yeah, I forgot that. This is what happens if you get lazy. So anyway, we talked about data conditioning. So now we're gonna move on. Yes, we're gonna talk about, so we just talked about data conditioning. How do we collect the data and what kinds of data we might want to use for the system, and the research that's been done in that direction. And so now we're gonna move on to the system analysis and how we might incorporate and combine the goodness of shared autonomy with these models, which we've already hinted at, and kind of what are actual properties that we care about and how can we design models and training procedures to kind of work in that direction. So for the shared autonomy case, we've already kind of touched on this, so I'll go quickly. In assistive settings, sometimes users prefer to have help, completing a task. You can also just make it easier to kind of compensate for maybe they can keep moving for some reason, and the robot can stabilize it, for example. So the way we talk about it in this line of research, or what people have done, is as confidence in the target grows, the robot kind of can take over. And what we're going to do is combine some magic belief that is gotten by systems designed to do so, to help us reach some sort of goal G with the action mapping output. So this allows for more precision, and it does require that we have a pre-trained action mapping model, and mappings of beliefs to the state action pairs in the data set. So I apologize for the change in notation, but all of these are the high dimensional velocity commands. This is not the same A as in previous slides. This is the high dimensional commands. And what we would do and what this would kind of look like in practice is that we're going to have some sort of weighting parameter alpha, which is going to say how much should the person's action be taken in and how much should the robot's action be taken in. Then we're going to have the actual actions that we're trying to blend together in order to complete some sort of problem. So this is kind of where like the robot taking in component comes in, where, as alpha changes, that decides how much is the robot in control versus how much is the person in control. And the last thing that we have is that, there's some sort of beliefs. We have some maybe discrete set of things that the person might want to grab in the scene that we're going to be able to define some sort of belief over. And the robot's actions simplistically are just going to be, how far off from this goal are we? So in terms of like, if we're dealing with velocity, so like joint angles, the goal would be, joint angles of the robot versus the target joint angles we'd want to see. And that's just going to be the action combined over the different possible goals that we'd want to reach. Right? So if that didn't make any sense and that was a bit too technical, we're just mixing two things together. And then this is how we're mixing it together on the more technical side.
This is interesting. So if I want to go here or here, the robot will drive me to the middle point.
Hypothetically, yes. As your robot's in the middle between the two targets, yes, but that's where you would probably have more control over the system once you made a decision. Do you go to the goal to the left, my left, or to the goal to my right? Yeah, so yeah, initially the beliefs should be kind of equal because you're equally far away. But then as we adapt, it'll kind of start being like, okay, he probably wants to go here. And also just how this is structured, I guess the magnitude is going to kind of increase in that and we'll weigh it less and less. Yeah. Question?
Just like two quick ones if you don't mind.
Yeah, of course.
So the belief effectively kind of like analogous to entropy then, like in the sense that like at the point of maximum uncertainty, you're half and half or whatever, like you're equiprobable. And then at the point of least uncertainty, you have like the robot, or I guess your belief about the goal is like 100%, like that's what the user wants to do.
I don't know if I use entropy. I'd say more like probability, but I guess that is related to entropy. And I don't remember the mathematical equations for some of these things. There's no log probability. I mean, I guess you could. Anyways, I think thinking of it more as a probability. So if you have like 5 items, and as it's adapting, you're doing a weighted sum over these 5 items, then yes, as you get closer, your probability is this is going to keep going higher and higher. So it's like a weighted sum if you normalize over 1. So like an expectation over distribution of possible beliefs or something. Yeah.
And does AR act as a sort of like if belief is then a probability, then is a subscript R sort of an expectation?
Yeah, so it's like the expected robot action given this is how much velocity or like finite difference velocity I have to take to get you there in like 1 step.
Right.
Weighted, yeah, so it's a weighted, yeah, so that's why I keep saying weighted sum, because that's kind of what an expectation is over the value affiliated with the belief at that current time step. Good questions, I like it. Yeah, this last point is just more on the technical side about does this thing actually work? And they prove some math showing that if you follow this procedure, it will reach the target that you care about. Right? So far, all the papers we've talked about or hinted at kind of make the same assumption when it comes to the actual model itself, which is we're going to use a typical multi-layer perceptron is, our usual choice for the decoder model. And so the way this works is you take your inputs, you take all your inputs, you concatenate them into a single vector, pass them through this model, and that is how, and then you just trust whatever this deep neural network is going to do it. And if there's something that you care about that the model should do, you're going to just trust that the data you've collected is good enough to kind of elicit whatever properties it is you think you care about. One issue with this end-to-end model approach is that it can suffer from drift. And if you don't know what drift is, drift in itself is not necessarily a bad thing, but in this context, it's not necessarily good. It's this problem that I pointed out earlier where this guy let go of the joystick and the robot just kind of veers off and floats and does its own thing. So without any input, the robot would just kind of keep moving. So the other thing that I would point out is that data distributions, particularly when you're doing, kinesthetic demonstrations and collecting them, is that they're not really robust in practice to contain any useful properties. And so if you have a useful property popping out of it, I would say that's more chance than, well designed. I guess you could also argue maybe you should generate procedures on how to best optimally collect data, but I just feel that generally, if you have to require more than one iteration, that's going to be problematic regardless. And so that's one way you could do it is here's best practices for collecting data. But the way we looked at it is, what if we just more intentionally, intelligently build a model that actually does things we care about from the get-go? And maybe this will mitigate some of these issues that we say are problematic. So first off, in order to do that, we need to know what are desirable properties we would like of a system. So the first property I'm going to mention is called controllability from the literature, where there exists an action sequence under the mapping to navigate between all states. So basically, even though we're losing information and we can't move everywhere, it would still be good if there was a way to kind of get everywhere in the world. Even if we have to do some sort of weird wonky-tonky trajectory to actually get to the same point, which would be different if we had full control of the robot. The next one is scalability or proportionality, depending on the papers, where larger action should lead to larger state changes and smaller action should lead to smaller state changes. So in practice, all this means that if I tap the joystick, the robot should move a little bit, and if I hold down on the joystick, we'd expect the robot to move a lot. Right? Consistency is the idea that action maps should behave similarly in nearby states. So if I'm standing here with my robot's moving like this as I push on the joystick, it shouldn't just suddenly veer off and do something weird. Another word you might use is smooth. And this is not so hard to enforce. There's this thing called lipschitzness that if you can enforce that, you're good. And there's a whole line of research, like 7 or 8 papers, probably more, talking about how to do this with neural networks. So we're not too worried about that. And the one that was more the focus of my own work and has been touched on in previous works is this action reversibility, which means it's possible to undo a user's action. So kind of what this can look like in practice, I show with this video here. So we have a robot arm, it moves a little bit, and then it comes back to roughly where it started. And then proportionality comes here, where larger action leads to a larger movement, and then it comes roughly back. So this is the embodiment of this reversibility and proportionality thing. So that's, I talked about these last 3 in a bit more detail. And part of the reason that's the case is because, well, I think controllability hasn't really been formally discussed in papers. I think there's ideas from control theory that touch on this exact property, reachable sets and this sort of thing, but there's a lot of math that goes behind it. And so I think formalizing and writing up what does that look like in the context of teleoperation is one potential idea that's quite promising. But again, there's a lot. That's the starting point, and there's more interesting things I think to be said once you first. What does the controllable reachable set actually look like? So that's great, but then how do we actually guarantee any of these things, right? So we say we want this magic list. We've said you can solve one of them using something called Lipschitzness, but what about these other ones? How do we actually guarantee any of these things will happen in our model? So before we say how we solved it, again, I will kindly request for those interested, what do you think we could do in order to enforce a model to do certain things that we want? So I'll give it a minute. I don't want to spend too much time because I have some slides I still need to go through, but yeah, we'll spend 10 seconds, 15 seconds. Constraint optimization, that is one promising way you could do it. So you do some online optimization procedure to say, I want these things explicitly. Good. All right, cool. So we're gonna move on. Oh, and regularization. All right, cool. So that was just some ideas about things we might do. And so if there's any questions about what we've talked at this point, check. All right, cool. So the solution we had to this is what we ended up calling the state condition linear models, or maps. So what does that mean? So what we're going to do is we're going to say that robot commands are linear with respect to the user input. So this little h here, for those who can see it, is a matrix, and the matrix H is going to be a matrix product with whatever the user's action is, which we're going to be set as this like vector, 2D vector for that kind of thing. But the key difference is we're going to say that representations of where this matrix H are coming from is going to be related to some nonlinear operation with respect to this robotic context OR. So we've now kind of decomposed the model from just giving everything to a single model to saying, all right, this inputs are going to then dictate what function that the user is actually going to control. And this function that's the user is going to control is something that we can start saying useful things about. And the reason we want to be able to do that is because by how this is set up structurally, this allows us to have a model that we know is going to be proportional, like in a single state, and give us, this low actions, low movement, high actions, high movement kind of property. It's going to be reversible because, linear map, if you take the negative, is going to go the opposite way. And it's going to be consistent, although that's something you can do for any kinds of models. Right. So one issue, though, is that the reversibility property isn't quite true, because since this thing is dependent on the states, you're going to have matrix H here, and then you're going to have another matrix over here, and these are not necessarily going to be the same matrix. So if I do the inverse action using this new one at the state that I moved to from this point, it doesn't actually mean that we're going to get back to where we started. And so it isn't actually obvious how to do that exactly, but using very advanced math, and we were able to prove that you will in fact get closer to this. So you may not exactly get back to where you started, but you'll get close. So we assume that there's going to be some sort of linear transition. So as like a dynamical system, we have velocity commands that we're adding to some current robot state. So that's where this transition comes from, or like a form of gradient update, if you prefer that words. The model has to be Lipschitz, so we have to be consistent in order for this property to make any sense. And that we find is that, taking the inverse action negative A at the state that you went to, you do in fact go closer to where you started, right? So just want to make sure that was clear as well.
So H is conditioned on the absolute joint pulse state, right?
Yeah.
So which makes it easier than if say H had been conditioned on the velocity vectors or something, because positive velocity vectors and negative have they to do, right? But if it's the same pulse.
Yeah, exactly.
It makes it easier.
Yeah, and this is why I guess you could think, as someone said, you could maybe condition on actions, but that's why it might cause problems for the system at deployment, right? Because you're like dependent on your own predictions. So,
Just 2 slides ago, it says that the robot commands are linear with respect to the user input, but the representation of mappings are non-linear with respect to the robot. I'm just having like for some reason my brain's just like choking every time it gets to that second sentence. I don't understand what it means by the mappings are non-linear with respect to the robotic context.
so that might just be a bad choice of vocabulary I use, so I apologize. But basically, this is this idea of what I was referring to called a hyper network. So for those who don't know, it's a model that predicts models. So the super model is this nonlinear neural network, which we don't really care, do whatever it takes to get good performance with it. But then the output of this is another function, which is this linear function H. So what I was trying to communicate, which I failed to do, is that the commands are linear with respect to H. So once we get a state once and we have H, we don't need this technically anymore. And the fact that we do this in our experiments is just out of convenience and trying to be kind of close to previous works. I can imagine settings where maybe you say you would query the person, do you want to change what H is at any given time given the current state? So that's kind of the idea, is that this decomposition is that this will give us a function. In our experiments, we're continuously updating this. We don't have to though. So we just need this once, and we can play around and let the user move it as much as they want without ever updating it again. So.
And is this hyper network, is it like, is it, I guess the word I'm looking for is fragile, like, is it very prone to like creating poor results under like non-optimal conditions? Because I feel like a lot of this network depends on that hyper network.
Oh, yeah, like the structure of the hyper network is very important for well, I mean, the way we structured it is why it works.
Right.
I think that's also why I mentioned that data set robustness and bad data can be problematic. In practice, we do find that our models are slightly better in the sense that they'll let you move something somewhat sensibly. Whereas if you take the end-to-end approach, garbage in, garbage out. And so those are much, much worse. And so this kind of acts as, I don't know, I'll say a regularizer. I don't know if that word rings with anybody, but it's like constraining the function class that the person's actually interacting with kind of makes it easier to get away with having bad data. But we don't have any like concrete, like, okay, if your data is this much noise or something, this is what you can expect. So,
I think maybe the key for the written the robot commands are locally linear with respect to input. So about every one state, that's when the matrix sets up a linear mapping so that your two joystick degrees of freedoms map to a particular linear combination of the robot motor commands. So two joystick axis maps to some vector of robot 6-dimensional or 7-dimensional motion in one way along the joystick backward, and then joystick sideways maps to another vector in that high dimensional space. But when you change, so as the robot moves around, you get a new age from a new state. So globally, everything is non-linear, right? If I were to push forward on the joystick, it would start going linear like that, but then over the global trajectory, it makes a curve. So I would, for instance, I could use a forward push on the joystick to do the sort of curved trajectory to go and pick something on a table.
Oh,
yeah. Thanks, Martin. All right, so yeah, so the last thing, just to kind of justify why did we do this. So this is video footage from one of our user studies, where we had asked participants to do what is called a pouring test. So to empty the contents of a cup into some bowl. And as you can see, he can easily kind of undo and redo what he just performed for the test. And we compared against this mode switching scheme that we hinted at and baseline like end-to-end approaches. So in terms of both success rates, where success is defined as could they pour the content out of the container into the target bin or not, and in terms of like subjective measurements using the NASA task load index, where lower is better. We generally find that compared to the typical end-to-end algorithm, that our model is slightly better in terms of performance from user perspectives because we move in the right directions, and this was statistically significant in terms of the median. So we had evidence suggesting this is a good idea, and we're going to gloss over the part that mode switching does work quite well. And just because maybe you've never seen this plot before, what we're plotting is called a violin plot for those who don't know. And just to kind of break it down just so that we're all on the same page, what we're plotting is like the sample probability density. So these curves represent, what is the probability that the samples are going to end up here. So the thicker it is, that means it's more likely going to be in that location. The middle bars are the mean performance. So just like, geometric average or whatever the actual terminology for that is. And then the bars of the tails here and here and everywhere else is just, these are the furthest points of our like empirical distribution. But the big takeaway is that our blob was lower than that blob, or our blob was higher than that blob. So this is just to kind of fill you into what exactly are we trying to communicate with this other thing. Right. So one issue though, with all this work that we did, and this is kind of starting to go into ongoing work, and I don't think we'll have too much time to delve into it, but just to kind of say the punchline is we did a better proof, where in the previous math, we only assume a single movement. So you push on the joystick once, robot goes here, and then you go back once, and then you'll go back. But in practice, what actually can happen is maybe you're pushing on the joystick in one direction for a while, so the robot keeps moving, moving, moving. Then you decide, I don't actually like the path that I've taken, so you push backwards, and you start going backwards and backwards and backwards. So our proof doesn't actually account for that setting. And so can we account for, not just a single step, but a trajectory, a sequence of actions? And the answer is, yes, we can. And a lot of the proof is basically the same, so I'm not going to dwell on it too much, but basically, Lipschitzness is always a good idea. Instead of doing a single linear update, we're going to do Euler integration. This is I don't know, I think it makes sense in practice because, there's this online loop where the person is sending commands in this way. So, this Euler integration assumption is more just, this is actually just what's actually happening. And again, the punchline is that the inverse action sequence, if we do the exact inverse actions, there's a lot of gray area with that, but it will roughly bring us closer within, some additional constraints, that this is the worst that we're going to do. And in practice, although I don't show the plots in here, we do find that that can be actually much lower than what the proof predicts.
Is it exponential?
Yeah, it's exponential. It's pretty bad. It's pretty bad, but it's not so bad in practice. In practice, it's not so bad, but it can get really bad. Right. So those were results, and I guess we're at time. So I'm going to skip over all the last bits of slides. The TLDR of all this is the thing we did in the last paper was the best idea. So in summary, data-driven teleoperations, there's lots of things to consider. Even if they're mostly just applied things like the data that you're using and how do you actually model the system. And there's lots of features and there's just lots of work that can be done, I think, to make these things better and go from being this kind of cute research idea to something that might be actually used in the real world by people to kind of, hopefully, at least in some small way, improve the quality of their lives. And so I believe, other data modalities, improving understanding of the system. And so that is my presentation. Thank you for those who stayed till the end. Thank you for anyone online. Thank you for anyone online for joining as well.